Welcome to Maths with EJD. We're still talking about differential equations, and we are getting into a dimension that is really interesting, talking about systems of differential equations. So just like in the case of equations, where we can have maybe just one equation, and where we say something like, say x plus 2 equals 7, and then we solve that, you know, and you just solve and you get x equals 5, maybe, and then you can graduate from that, and then you have maybe x plus y equals 2, and maybe x minus y equals say 0. Okay, this becomes a system, and you have to solve the two simultaneously to get your result. So I mean, if you solve this simultaneously now, you get x to be equal to 1, and y is also equal to 1. Okay, so this is a system of equations now. So just like we have this, we have the same for differential equations. Okay. And this video is an introduction to that. So in the next 5 or 6 videos, we'll be talking about system of differential equations and different aspects of that. Okay. So let's go for that now. Okay. So imagine, okay, let's have an overview first of all. A system, a system of differential equations, a system of differential equations consists consists of multiple multiple interrelated interrelated, you can even say interconnected or even coupled interrelated differential equations. Okay, interrelated differential equations that that describe how a set of dependent variables, a set of dependent variables change when change, right? With how they change respect with respect to an independent variable. Okay. Oftentimes, so such systems model complex complex dynamical behaviors, complex dynamical behaviors in various scientific and engineering disciplines. Okay, so some real world situations like that can help us see how interrelated concepts connect together. So let's look at a definition for this. Definition of a system of differential equations. So we can say a system of n first order, a system of n first order differential equations. We restrict it to first order. You can have other orders. A system of n first order differential equations can be written as, check this out, the the x1 dt equals f1 of x1, x2 up to xn, and of course it's also a function of t. Then you have the x2 dt equals f2 x1, x2 all the way down to xn, still with t again. And then that can go on. So you can have 3 by 3, you can have 3 equations, you can have 4, you can have as many as you want. And it goes all the way down to n equations, the xn, the xn, the t. So you have the xn, the t now equal to fn x1, x2, all the way down to xn again, t. All right. So you have, so this is the system we're talking about now. So you can have all those interconnections. So we can say, so we say where each function where each where each function fi defines how xi evolves, over time. Okay, so that takes us to classification. So classification of system of differential equations. So the first classification is a linear system. So you can talk about linear system. So you can have linear system of differential equations. So if each equation is a linear combination, of dependent variables and their derivatives the system is linear. Okay, so the general form is x dot equals ax plus b of t. This is the general form of a linear system. Okay, so that means you can have x1 equals a1x plus b1t and so on and so forth up to xn equals anxn plus bn of t. Now, that's for linear system. We can also have the system to be non-linear. So we can have a non-linear system of differential equations. So we have non-linear system. So from our previous knowledge, we know when there's non-linearity, it means we have one of the derivatives is multiplying the derivative. I mean, one of the derivative, the dependent variable is either higher than is of order one, or it's multiplied by one of its derivatives, something like that. So if any equation involves nonlinear terms such as products of variables, okay, or nonlinear functions, e.g., maybe you now have sine, you have sine, you have exponents or exponential. Okay, the system is nonlinear. Okay. Yeah, at this juncture, let's talk about some basic examples. So basic examples of systems of differential equations. All right, basic examples of systems of differential equations. So let's start with physics. So in physics, we have coupled spring mass system. So the interesting thing again here is that a second order differential equation, for instance, can be broken down into a system of two first order differential equations. We saw that when I was doing a numerical method for partial differential equations using shooting method. That's the basic idea there. So here we have two masses connected by springs. Two masses connected by springs obey Newton's laws, as follows. So you have m1 d squared x1 dt squared equals minus k1 x1 plus k2 into x2 minus x1. You have that. You also have, so m2 d squared x, this, this is d squared x1. So this is d squared x2 dt squared, and that is equal to minus k2 into x2 minus x1. So these two together now gives us a system of differential equations. So this is actually second order, a system of second order differential equations. So that is what the masses connected by springs, which obey Newton's law. That's what that gives us. So this forms a linear system. It forms a linear system when rewritten as a first order system, Okay. Then number two, so number two, we have something like this in biology. So for biology, right, we can have the in biology we have the predator-prey model, predator-prey model. So for the predator-prey model, we have the t equals ax minus bxy, and we have dy dt, which is equal to minus cy plus dxy. So here we say, of course, this is another system. This is a very popular system in ecology where X is the prey and Y is the predator. I mean, that this is like this is my core area of research, for instance, and maybe along the line I'll get to talk about mathematical biology and all that. So, uh, prey and predator interact non-linearly. Okay, they interact non-linearly. So we have a third example. We have a third example in engineering, especially electrical engineering. So talking about RLC circuits, reactance, inductance, and capacitance circuits. Okay. So this is in engineering. So where Kirchhoff's Kirchhoff's laws rather, Kirchhoff's laws yield the following, where we have L di dt plus Ri plus 1 over c integral of I dt always equal to V of t. Okay, so now you see these i's now. It could be L d1 dt, you know. I mean, you just, okay, this is, yeah, so you can have this into a system of equations like that. So that's another example. So you can also have two species. This back to biology now. In biology again, another biology example. Okay. Um, this is more like more like a broad-based worked example. I think I want to take the liberty to deal with this. Okay. Um, more like a worked example. So consider consider two species, competing competing for the same resource, for the same resource. Okay, that's a biological thing, right? But we can translate it to math this way. So we have dx dt equals r1 of x into 1 minus x plus alpha y all over k. And then you also have dy dt. So we have two species now competing for the same resource equals r2y now into 1 minus 1 minus y plus beta x all over k, like this. So this is a competition system. So where R1, R2 are actually growth rates. They are our growth rates. K is the carrying capacity. K is the carrying capacity. Of course, unlike the population growth. When we're doing first order systems, we saw exponential growth, which is unrealistic because there's limits to the space even available for species to grow. But this is more realistic because K is the carrying capacity, meaning that the environment can only carry so much, can only afford so much space. And alpha, beta measure competition. So they measure competition. So with this example now, we can do some basic things like solving for equilibria. So we can solve the system to get the equilibrium point. That's what some other people can call steady state, where the system is in a stable, so to speak. So we have the x it equals 0 and the y the t equals 0. So you're setting the x dt equals 0 and the y dt equals 0. That means that each of this is just equate to 0 and do some kind of solving, right? That's how to get the equilibrium point. So setting this to 0. So we find equilibrium points. We find equilibrium points as follows. We have a trivial equilibrium. Trivial equilibrium. So trivial equilibrium is that place where there is extinction, that the two species X and Y both go to 0. They are both 0. If you solve that, you find that. Number two, you can also have a single species. You can have a single species equilibria. Single species equilibria. In this case now, X and Y can be either K0. It means that the first species persists and takes over the whole system because K is the carrying capacity, and the second species goes extinct. Then you can also have XY equals 0K. 0K meaning that the first species goes extinct while the second species takes over the whole environment, the whole system. Then number three, you can actually have a coexistence equilibrium. Coexistence equilibrium. So in this case, you have the two species, reaching some kind of balance. The two of them actually persist. Okay. So here, this is like K into 1 minus alpha all over 1 minus alpha beta. If you solve that system, you're going to get this. So you have K into 1 minus beta all over 1 minus alpha beta. So this is of course, this is only possible if feasible. If feasible, okay. So it may not be. It may be able to derive it mathematically, and it may not be feasible biologically. That's what this means. So this means that both species go extinct. That's what this means. Both species go extinct. Then here, here, species species X species X persists, and here then species Y goes extinct. And then when we come here, so this tells us that species X goes extinct and species Y persists. Okay, that's what this means. But in this other case, both species persist. Species both species persist. Okay, that's what that is about. Now, there are other things we can do here, but we are in previous subsequent videos we can do all of this. So by analyzing stability, using Jacobian matrices, which I'm going to talk about maybe later, maybe not immediately in this playlist, but at some point down the line, we'll be talking about that. By analyzing stability using Jacobian matrices, we determine we determine species survival or extinction conditions you know, talking about stability and the rest of that. Okay, so with this we come to the end of this introduction to system of differential equations. All right, let me know how helpful these videos are for you in the comment section, either on Facebook or on YouTube. Let me also know if there's a topic you'd like me to teach or a problem you'd like me to solve in any aspect of maths or Python. If I'm able to do it, I'll, get to it. Then, of course, if you have not subscribed, please go ahead and subscribe. And everybody, don't forget to hit the notification bell so you can always get alerted each time any video is released. So subsequently, I'll be talking about other aspects of system of differential equations. So like and share also so that more people can have access to this great content. Till I come your way again, keep doing math right. Bye.